Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to discuss the inner product and its relationship to the angle and orthogonality. So in this topic we're going to examine the relationship between the angle between vectors and the inner product, and then we will make some observations about the inner product and orthogonality. Now, recall that given these two-dimensional vectors u and v, their inner product is defined as the product of the first entries plus the product of the second entries. Alright, now let's look at these two vectors, and as we see between them there is an angle. Let us assume, of course, that neither of these vectors is the zero vector. Now, recall from secondary school your aide-memoire SOHCAHTOA. Specifically in this case, cosine of theta is equal to the adjacent over the hypotenuse. In this image, we have that this is the line segment AB over the line segment AC. Now, for this to work, you must remember that the line segment AB may result in a negative number. Thus, we can create the following right-angled triangle where the hypotenuse is the 2 norm of u, or the length of the vector u. The adjacent is a scalar multiple of the 2 norm of v. The thing is, we have to figure out what that scalar multiple is. Thus, we have that cosine of theta is equal to the line segment AB over the line segment AC, or an appropriate scalar multiple of the 2 norm of v over the 2 norm of u. Question: what is the appropriate value of s to produce that right-angled triangle? Now, a quick review. From a previous topic, remember that v minus u is the vector pointing from u to v, as is shown here in this image. I'm re-emphasizing this because it's ever so slightly counterintuitive, because it seems that v minus u should be the vector pointing from v to u, but it's actually the other way around. So, v minus u is the vector pointing from u to v. Therefore, s times v for any scalar is the vector pointing from u to that scalar multiple of v. Now, we want that scalar multiple of v right there that forms that right-angled triangle. That is, we want that scalar multiple, if you take a look at the image, to be that scalar multiple of v such that the length of the difference, or the vector from u to s times v, is minimized. Now, why is that? Well, we can actually deduce that from the Pythagorean theorem. The Pythagorean theorem says that if we have a right-angled triangle, then the hypotenuse is always greater than either of the two edges. And therefore, s times v minus u, if that does not form a right-angled triangle, will form a vector that is longer than the appropriate scalar multiple that forms a right-angled triangle. Thus, we must first find s times v minus u, and then subsequently we must find the 2 norm of that difference so that we can minimize it. Well, s times v minus u is just the vector v times s minus the vector u. But the scalar multiple of the vector v by s is just s times each of the entries, and the difference of two vectors is just the difference of the entries. Alright, so now we have s times v minus u, and we can calculate the 2 norm. We want to minimize that 2 norm, and the problem is, unfortunately, that 2 norm also includes a square root. However, we're going to go back to secondary school to solve this problem. Now, Another review from secondary school. If we have a function f at s that is both positive and negative, then the minimum of f at s may not actually be the minimum of f at s squared. So for example, here we see s squared minus 1. That has a minimum at s equals 0. But if we square that function, then that point, s equals 0, is no longer a minimum. It's actually a local maximum. The new minima are at plus or minus s equals plus or minus 1. However, if the function is non-negative, that means greater than or equal to 0 everywhere, then the minimum of f of s is also the minimum of f of s squared. So here we see a function that is strictly positive, and when we square that function, we see that the minimum of f of s is the same point of the minimum of f of s squared. Why are we doing this? Because we're going to square the Thus, rather than finding the value of s that minimizes an expression that has a square root, we are now finding the minimum of this expression here, which is just a quadratic. And remember that u and v are given, so u1, u2, v1, and v2 are known values. The only unknown is s. So let's expand those and collect on s. We see that this is, it's a quadratic in s. And it is concave up. Why? Because v1 squared plus v2 squared is strictly greater than 0, because we assumed that both vectors u and v were non-zero vectors. Alright, so now we have a quadratic in s, and we want to find where the minimum is. But wait a second. From secondary school, you know that if I have a quadratic of the form a times s squared plus b times s plus c, that has a minimum when s is equal to negative b over 2a. Alright, so what is negative b over 2a in this case? Well, s is equal to negative b over 2a. Notice that the minus signs cancel and the 2's cancel, and so we're left with this expression here. What's in the numerator? u1 times v1 plus u2 times v2. Thus we have that the appropriate scalar multiple of v is given by the following expression. And looking at the denominator, we can simplify that to just being the 2 norm of v all squared. Alright, therefore going back, cosine of theta is s times the 2 norm of v over the 2 norm of u. Substituting the value of s into the expression, we get the following. However, notice that the 2 norm of v cancels with the one of the 2 norms in the denominator. And simplifying this expression, we get the following. u1 v1 plus u2 v2 over the 2 norm of u times the 2 norm of v. That's the inner product of u and v over the product of the 2 norms. Therefore, cosine of theta is equal to this expression, or in other words, theta can be found by taking the inverse cosine of this expression, and therefore the inner product can alternatively be calculated using the product of the 2 norms times cosine of the angle between the 2 vectors. Now, recall that we assumed in this derivation that neither u nor v was the 0 vector. Therefore, for the inner product to be 0 in this case, that's true if and only if the product of the 2 norms times cos theta is equal to 0. But because u and v are neither the 0 vector, the 2 norm of u and the 2 norm of v must both be strictly greater than 0. Therefore, cos of theta must equal 0, and therefore the angle between the 2 vectors must be 90 degrees, or pi over 2 radians. Also, additionally, we will say that u and 0 are orthogonal for all u as well. Why is that? because the zero vector gives us no information about any other vector that is two-dimensional. Therefore, we will say that the inner product of u and v is equal to 0 if and only if u and v are orthogonal. Thus, we have derived the following formula for the inner product. This is an alternative formula because the other formula is actually very easy to calculate. It's just the sum of the pairwise products of the entries of the vectors u and v. Therefore, it's easy to determine if two vectors are orthogonal or nearly orthogonal. Later, we're going to see that there's other definitions of the inner products for other types or classes of vectors, but we will always define the angle based on this definition of the inner product. So in summary, in this topic, we have seen that the inner product is critical in determining the angle between two vectors. We've observed that this is a very fast test also to see if two vectors are orthogonal. Is the inner product equal to 0, yes or no? And it is actually really easy to calculate the inner product from the formula. It's simply the sum of the pairwise products of the entries of the vectors. We will see that this continues to hold for three-dimensional vectors, and this will also hold for other vectors that we look at throughout your first course on linear algebra. Here are some references, acknowledgements, the colophon, and a disclaimer. Cheers!